All right. Well, welcome everyone. My name is Ian Manley, and I'm covering for Dr. Mazine today. I'm one of the TAs for this course, so if you don't know me. So what we're going to be talking about today is section 4.4 called tangent planes and linear approximation. So I don't know if this has been emphasized to you in the previous lectures or not, but Calc 3 has a lot in common with Calculus 1. In Calculus 1, we had a variable, or a function of a single variable, and we wanted to know how limits work with that, how to take derivatives of a function of a single variable, and how to integrate functions of a single variable. And then we learned a bunch of things that we could do with those techniques. Calc 3, all we're doing is we're taking functions of more than one variable, and we're trying to do all of the same things, limits, derivatives, integrals, and all of the different things we could do with those. So right now we're in the middle of learning about how derivatives work with functions of multiple variables. And so we learned about partial derivatives last time, right? So now what we're going to do is we're going to try and do some of the things we did in Calc 1 with derivatives, only now we're doing them with partial derivatives. So one of the things we were able to do with derivatives in Calc 1 was find the tangent line to a function. So this is Calc 1. So if we have our axes here, and we have some sort of function f of x like that, we could pick a point A, an x value, and we could find the tangent line to this function at the point A. So that would look something like this. And a tangent line is a line that kind of just barely touches right where we are on the graph and just continues on its way. And it's going in the same direction, loosely speaking, or has the same slope as the graph at that point. And if we wanted to know the equation of this tangent line, it would be y equals f of a plus f prime of a times x minus a. That's the tangent line. But we're finished with Calc 1 now. We're trying to do Calculus 3. And rather than have a tangent line, now we're going to have a tangent plane. So if I draw some sort of 3D shape, so we have our 3D axes, maybe let me draw like an ellipsoid or something. Is that this? I could come all the way around. We have that. Very bad looking ellipsoid, but we have a point on that ellipsoid, and instead of having a line just barely touching there, we're going to have some sort of plane that just barely touches that point and kind of continues on forever, and it's, loosely speaking, going in the same direction as our function at that point. And we have a formula for that plane that looks a lot like this right here. So if this point on the xy plane is at the point AB, kind of like how over here we had our function at the point A, then the formula for our tangent plane is going to be z is f of AB, so kind of like how we had the f of a over there. And then we have plus the x partial derivative at AB times x minus a, and then we have the y partial derivative at that point times y minus b. And that part kind of mirrors this right here. So we have a derivative times x, the independent variable minus the point. Here we have that, but that's just for, we have it for one for x and one for y. So that's the theory of what's happening here. Why don't we actually do an example and see how to actually compute these things. So I've never done this before. I don't want to break anything. Okay, thank you for letting me know about that. Oh, there we are. Oh, awesome. Okay, that was close. All right, so I wrote down an example. So let's say that we have z is e to the x times sine of y. And we want to find the tangent plane at the point 0, pi over 3. So I'm not exactly sure what this shape would look like. It's a lot more complicated than the shapes we've been dealing with before because it's not made of a polynomial. But we could still compute what the tangent plane is here. Okay, well, the first thing we need to do is we need to figure out what our partial derivatives are going to be. So we need to know both the x partial derivative and we need to know the y partial derivative. So let's start doing that. So we need to know partial z, partial x. Well, when we're taking the derivative with respect to x, sine of y, there's just going to be some constant. So really all we're doing is we're taking the derivative of e to the x, but we all know the derivative of e to the x is just e to the x. So this is just e to the x, and then we have sine of y left behind there. So it's actually the same as the original function. And then for the y derivative, that'll be a little different. All right. Well, now we leave the e to the x alone. That'll be our constant. And we'll take the derivative of sine of y. So we have e to the x, and then the derivative of sine of y is going to be cosine of y. So those are our partial derivatives. So we know those now, and according to the formula up there, we need the partial derivatives, and then we need f of ab. Now I said this was z equals e to the x sine of y, but really I could also write f of xy is e to the x sine of y. And this 0 here is our a, and that pi over 3 is our b. So that's where we're finding the tangent plane. So we need to know f of ab. So that's f of 0 and pi over 3. Well, we just plug that in. So we have e to the 0 times sine of pi over 3. Well, e to the 0 is 1. And then sine of pi over 3 is going to be root 3 over 2. So this is just root 3 over 2. And not only that, but we do need to know what the partial derivatives of this function are at the particular point. So we have our x partial derivative at 0, pi over 3. Well, we're just going to plug it in to this. But that's the same as plugging it into the original function. So we already know what that's going to be. It's going to be root 3 over 2. And then lastly, for fy, that's 0, pi over 3. That's going to be e to the 0 times cosine of pi over 3. Well, that's going to be 1 times 1/2 is 1/2. All right, so now we have all the ingredients we need to form our tangent plane. So let me try and flip this one up now. There we go. Getting the hang of this. Don't want to crash. All right. So we can use our formula, which I guess I just covered up, but it is z is going to be f of ab So that's going to be root 3 over 2. And then we have plus the x partial derivative, which it looks like that's also root 3 over 2. But then that's times x minus our a value. And in this problem, our a value, or our x coordinate, was 0. So we have x minus 0, or you could just write an x, it's no big deal. And then we have the y partial derivative, which is 1/2, and we have y minus the b, or the y coordinate, which is going to be pi over 3. And there we are. Here is our tangent plane. So kind of like the tangent line in Calc 1, the tangent plane is a good approximation of our function nearby the point 0 pi over 3, or really any other point that you would want if you found the tangent plane there. Now, one thing that may come up in the future for you guys is finding the normal vector to your tangent plane, because it is a plane, so we should be able to figure out a normal vector to this plane. Now, the usual way we do that is for our normal vector, we take the thing that's in front of the x, the thing that's in front of the y, and the thing that's in front of the z, or the coefficients, and we make a vector out of those. So that's exactly how we're going to do this. So we're going to subtract all of this stuff over to the side with the z to see what our coefficients are going to be. So I have z minus root 3 over 2, and then we have minus root 3 over 2 times x minus 0, minus 1/2 y minus pi over 3, and that's equal to 0. So now we have our plane in standard form, so we could just read off what the normal vector is going to be. So there's like a 1 right here. So our normal vector to our plane, well, we have the thing that's in front of the x right here, so that's negative root 3 over 2. We have the thing that's in front of the y right here, that's negative 1/2. And then we have the thing that's in front of z, which is going to be a 1. So this is the normal vector to tangent plane. All right, so that's how we figure out what's going on there. Do you have a question?
Is there really a case where like z wouldn't be 1?
Where z wouldn't be 1? Actually, no, there's not. And let me give you the general formula for finding this normal vector, because there's really just a formula for it. So let me put this down now. So for any function, z equals f of xy, the normal vector to the tangent plane will be n, and it's going to be the negative of the partial derivative of f with respect to x, which is what we saw. It was negative root 3 over 2. We have negative of the derivative with respect to y. That's how we got that negative 1/2 as opposed to a positive 1/2. And then we'll just have a 1 there no matter what. So you were right. It's going to be a 1 no matter what, provided we have z as a function of x and y, which we often will. So that's how we figure out the normal vector. We don't even need to make up the tangent plane at all. We could actually just figure out this normal vector right off the bat if that's all they wanted. And sometimes they may want you to find a line that is perpendicular to a surface, and this would be the slope of that line. So that would be how you would use that. Okay. Any other questions before we move on here? Okay, so we found tangent lines in Calc 1, but why did we do that? I mean, other than they asked to. Well, a good reason to find a tangent line is, like I said a few minutes ago, you may want to approximate a function at a value nearby something you know. Like you may recall in Calc 1, they had you do problems like approximate the square root of 4.1. And in that case, you would use the knowledge of the square root nearby. Like we know what the square root of 4 is, it's 2, and we would combine that with our tangent line to figure out, at least an approximation, of what the square root of 4.1 was. So we're going to do the same thing only with multivariable functions now. We're going to try and approximate strange values of these multivariable functions. So let's say, so here's a problem. We need to approximate the natural log of 1.1 times cosine of negative 0.2. I don't know about you guys, but I have no idea what ln of 1.1 is. I have no idea what cosine of negative 0.2 is, let alone having them mashed together. But I do know what ln of 1 is. I know ln of 1 is equal to 0. And I do know what cosine of 0 is, which is nearby negative 0.2. I know cosine of 0 is going to be 1. So I could use that information to help me approximate this. So all we need to do to approximate this is find the tangent plane to a function. So our function is going to be that only with variables. So we have ln maybe of x times cosine of y. So that's our function that we're going to find the tangent plane of. And our a and b are going to be the numbers that are going to be close to these, where we know the value of those functions. So in our case, a is going to be 1, and b is going to be 0, because those are going to be close by our 1.1 and our negative 0.2, respectively. So now that we have this, we can find the tangent plane to f at the point AB. So let's go through that, how to do that. So in order to find the tangent plane, we need to know the partial derivatives of our function. So we know partial f, partial x. Well, let's see here. So we can leave the cosine of y alone when we're doing an x derivative, and we could take the derivative of ln of x. So it's going to be 1 over x times cosine of y. And then if we're doing partial f, partial y, we leave the ln of x alone and take the derivative of cosine of y. So we have negative ln of x sine of y. So those are our two partial derivatives there. Let's see. Put that up. Put this down. Okay. Yeah. And we also need to know f of AB. So f of AB, well, in our problem, that's f of 1, 0, because those are the points nearby where we wanted to approximate. Well, that's going to be ln of 1 times cosine of 0. Now, ln of 1 is equal to 0, so this whole thing is just going to be a 0. And then the last thing we need to do to get our tangent plane is we need to plug in a and b, or 1 and 0, into our partial derivatives. So we're going to have fx at 1, 0. Well, let's see here. Our x derivative was 1 over x cosine of y. So we have 1 over 1 times cosine of 0. That's going to equal 1. And then for the y derivative, we're going to have fy of 1, 0. Well, let's see. That was negative ln of 1 times sine of 0. That will just be 0. All right. Now we have all of our ingredients, and now we can construct our tangent plane, and then hopefully that will allow us to approximate this function. So our tangent plane is z is f of AB plus fx at the point AB times x minus a. And then we have the same thing for the y, plus fy of AB times y minus b. And like I said, we have all the ingredients we need to fill in that formula. So we have z, well, let's see. F of AB, we figured that out, was 0, plus fx at AB, that was 1, times x minus a, which was 1. Then we have the y derivative at 1, 0, but that was just a 0. And then we have y minus 0. All right, well, this is a pretty nice tangent plane. It's not too complicated. We have z is x minus 1. So that's all our tangent plane ends up being here. And now how do we approximate that function, or that value up there, ln of 1.1 cosine of negative 0.2? That's when we plug in the point 1.1 negative 0.2 into our tangent plane. Well, that's not going to be hard. We have z is 1.1 minus 1, and the y didn't play a role at all, so we don't even need to plug in negative 0.2 anywhere for this. So this leads us to believe that we have 0.1 as our approximation for what this function is. And that kind of makes sense if you look at what that function is. So ln of 1 is 0, so ln of 1.1 won't be too far away from 0, and neither is our answer here. So this is the approximation of ln of 1.1 cosine negative 0.2. It's about 0.1. If you throw it on your calculator, it'll probably be something else, but it won't be too far off from 0.1. It'll be within the realm of reasonableness. Anyways, anyone have any questions on how we did this one? Okay. Anyways, and yeah, you could use this method to approximate any strange value of your functions. All right. So now that we're a little more comfortable with tangent planes, we're going to talk for a moment about differentiability of our multivariable functions. So remember from Calc 1, and I'm going to be saying this the whole time because this class is almost like a copy of Calc 1 in a certain way. In Calc 1, we had a few functions that were sort of bad functions. We couldn't take the derivative of them at certain points. And the most common example of that is the absolute value function from Calc 1. So another Calc 1 analogy. oops, oh, still works, but I want to make the picture good. There we are. So this is the absolute value of x. I think everyone's familiar with what that looks like. So why wasn't this differentiable? Well, here the derivative would be -1 because it's just a line sloping down, so we just take the slope of that line, and that slope is -1. On this side, we would say that the slope is 1. But when they try and meet in the middle, this side's saying, oh, the derivative should be -1, and coming from this side, from the right, we're saying that the derivative should be +1. So when they meet at this little kink down at 0, 0, they can't really agree on what the derivative should be, so the derivative does not exist at 0. Because, and the geometric reason is that the tangent lines coming in don't agree. And for a differentiable function, we want the tangent lines at a particular point to match up with one another. We want to make it so there's only one tangent line, or as is going to be in our case, we want to make sure that there's only one tangent plane at each point. So let's look at a bad function in Calc 3. So a bad function in Calc 3 would be our friend the cone. So we have our three-dimensional coordinates here, and then we have a cone. Like that. And I'm only going to take the top half of the cone. So I'm going to have z is the square root of x squared plus y squared. So this cone actually has a lot in common with our absolute value function. Because if we're coming down maybe this side of the cone, let's say we have a point right there, the tangent plane is going to look something like that. You kind of plaster a plane on the side of this cone. But if we look at a point on the other side, our tangent plane is going to look kind of like that. And that's all well and good when they're on their sort of respective sides of the cone, but when they come in down towards the origin, they can't really agree on which direction they're going to slant down. Like this side, oh, I want to slant down like this, but then this side is, oh, I want to slant down coming down this way. And just like the tangent lines couldn't agree right here, the tangent planes over here won't end up agreeing. So this function here is not differentiable at the origin. Kind of like the absolute value of x. So this is sort of leading us to believe that if we want to call a multivariable function differentiable, we need it so that there's only one tangent plane and we're not having these different things kind of collide together. We also want to make it so that our function agrees with our tangent plane when we're really close to a certain point. So there is a rigorous mathematical definition to it, and it's the same one you'll see in the book, but I'm going to try and explain it in English because it's kind of complicated. So let's write down the formal math definition of what it means for a multivariable function to be differentiable. So let's see. A function f of xy is differentiable at the point x naught, y naught, so that's a particular point, if for all points xy near x naught, y naught. And when I say the word near, I mean, obviously, I mean close by. That's what near means. But more technically, I mean within a delta ball. So did Dr. Mazin talk about those delta balls before? Was that something that he mentioned? No? Okay, well then forget about it. Yeah, you could just think of near. These XY points are near these ones. They're just close by, intuitively. So if for all the points near the point that we care about, we have the following equation. Our function is going to equal this. All right, X naught, Y naught. All right, so let me explain what all of this is. So we're saying that our function is equal to all of this stuff. And what is the thing that I just underlined? That's right, this is the tangent plane. So the only thing I've done differently here is I've used X naught and Y naught instead of A and B. But then we have this extra thing over here. This is called the error term. And what this is this is the difference between f of x, y, and its tangent plane. So this equation is starting to make sense now because we have a function which is its tangent plane plus some leftover stuff. And we have a special thing that this needs to satisfy here. So let me write that on the next board here. So this e of xy can't just be anything. It needs to be something in particular. Or it needs to satisfy something in particular. We need that the limit as xy goes to x naught, y naught of e of xy divided by the square root of x minus x naught squared plus y minus y naught squared is 0. Now what this is saying is that as we get closer and closer to the point that we care about, our error term is going to 0. We want to make sure that once we hit that point that we care about, x naught, y naught, there's no difference between our tangent plane and our function. And that makes sense because the tangent is supposed to equal the function right at the point it's defined at. So we want that to happen. And this limit might seem kind of mysterious, but there's a Calc 1 version of this limit, which looks a little strange, but it's a bit more digestible than that. The Calc 1 version of this is the limit as x goes to x naught of f of x minus f of x naught over x minus x naught minus prime of x naught is 0. That's the Calc 1 version. And that you might be like, I never seen that before either. But what was really happening is if I move this over here, that's just the definition of the derivative. Because this thing right here, this is the definition of the derivative. And we want the difference of this and our actual derivative to be 0. We want this limit to actually exist and be the derivative. Loosely speaking, that's what this is saying over here. Like this is the distance from the point to the point we care about, as is that right there. Now this is the more technical definition of derivative for multivariable functions. But if you really want to understand what a derivative is, all you need to do is just look at those pictures that we had. So if you're ever in doubt, don't think about this one. This is the rigorous technical version. just, oh, where did it go? I'm not used to these boards yet. Oh, damn it. Okay, well, I erased the cone and the absolute value, but think of those. If your graph has any kinks in them, like it has any sharp edges or anything like that, you're not going to be differentiable there. But otherwise, if you're smooth and your function doesn't have any sharp points or gaps or anything, then your function's going to be differentiable, regardless of that crazy formula I wrote down. Oh, damn it. All right, there we go. Okay. So that's that. And finally, in my last few minutes here, I want to talk about what are called differentials. So you guys may remember differentials from Calc 1. So in Calc 1, if we had y is some function of x, and we could take the derivative of our f, then we would say that the differential df is the derivative of the function times dx. And that might seem kind of silly, because in Leibniz notation, these are fractions, so you just cancel them out and you get df. That's pretty clear. But what is this really saying? This is saying that if we have a small change in input, this is telling us what the change in output is. So if we vary the x by just a tiny bit, maybe instead of plugging in 0, we plug in like 0.1 or something like that, this formula will tell us how much our function value will change. So maybe changing the input by 0.1 changes the output by 0.2. And that will all depend on what the derivative is. So that's the Calc 1 version. The Calc 3 version is very similar to this. So in Calc 3, if we have f of xy now as our function, and we could take derivatives of it, it's differentiable, then we have that df is partial f partial x times dx, but then we also have the y as well. We have plus partial f partial y dy. So that's our new version of the differential. So once again, these things right here represent a tiny change in the input. And then this right here is a change in the output. And the amount that the output changes depends on how big our partial derivatives are. If our partial derivatives are really big, even a tiny change in the input will result in a large change in the output. So it all depends on the size of our derivatives. And this thing right here, this has a name. This is called the total differential. And the total differential has more uses than just measuring changes in input and output. The total differential will also be used next time in section 4.5 when we learn about the multivariable chain rule. Now, kind of like the chain rule in Calc 1, the multivariable chain rule can be kind of complicated, but if you understand what the total differential is, then it'll be easier to use the multivariable chain rule. So that will show up starting next time. So there are things that we could do with just the total differential. But first of all, let's practice finding it. So let's say that my function f of xy is equal to, let's see, I have a good example here. f of xy, let's say it's equal to e to the xy sine of x times cosine of y. And I want to find the total differential df. And it's called the total differential because it takes into account all of the input variables. It's not looking at just x or y, it's looking at the change in both x and y. So we need to find df. Well, the formula for df is we need to know both of the partial derivatives of this function. So let's do that. Let's see, so partial f, partial x. Well, let's see, so unfortunately we're going to need to do a product rule for this. So I have this as a function of x and that as a function of x. So first I'm going to take the derivative of e to the xy. And since y is a constant in the exponent of my exponential function, it'll come down here. So I have y e to the xy. I leave everything else alone. And then now I leave my e to the xy alone, and I take the derivative of sine of x, which will be cosine of x. And the cosine of y kind of just goes along for the ride because it is a constant. Then we have partial f, partial y. So now the constant in my exponential is the x. So when I take a y derivative, everything with an x is my constant. So that will be x e to the xy. I leave the sine of x alone entirely because it's a constant, and then the derivative of cosine of y will be negative sine of y. And then now I'm going to do the other piece. Oh, wait, oops, I took the derivative twice, doing the product rule here. Okay, so we're going to leave the cosine alone. Sorry about that. Now we're going to take the derivative of that cosine, which will be negative sine, and we leave the e to the xy alone. There we go. All right, so those are my partial derivatives. And now I'm going to stick those in my total differential. So df is the partial derivative with respect to x, so all of this stuff, e to the xy, sine of x cosine of y, plus e to the xy, cosine of x cosine of y. And that's times a dx. And then I have the same thing, only for my y derivative. Cosine of y minus e to the xy sine of x sine of y. And that's times a dy. So what this is saying is if I want to measure my change in output of my function, I would need to know the changes of input in my x and y, and then I would need to have specific values for x and y. And then I could figure out the change in it. So here's another example of how these are going to work. Push out a little more. Okay. So let's say that I have a cylinder of radius 5 feet and height 10 feet. And let's say I measured these things, but there's a possibility that I made a mistake in my measurement. Maybe my tools just have the inherent possibility of error, or maybe there was human error. But the error in the radius, so dr, can be up to 0.1 feet. And the possible error in my height can be up to 0.2 feet. That's the maximum error that we can have in each of the inputs. So what's the maximum possible error in the volume? So I could figure out the volume of this because I know the radius and the height, but because I might have an error with those, I'll probably have an error with my volume as well. So we're going to use total differentials to figure out what the error for my volume could be. Oh man, I'm running out of time. So we have V is pi r squared h. That's the volume of a cylinder. And I need to take my two partial derivatives of this to do the total differential. So I have partial V, partial r. Well, I'm going to use the power rule, bring that down. So I have 2 pi r h. And then partial V, partial h. Well, all I have in here is just an h, so it's going to be the constant next to it, which will be pi r squared. So the total differential here, dV, is going to be the r derivative, 2 pi rh, times dr. And then we're going to have the same thing with the h derivative. So we have pi r squared dh. And now since I know r, h, dr, and dh, I can plug all that in and figure out my dv, which is my possible error. Well, let's see. So we have 2 pi, r was 5, h was 10, and dr was 0.1. Then I add in pi, I have r squared, which is 25, and then I have dh, which is 0.2. All right, and then I could do all the arithmetic here. 2 times 5 times 10 is 100, times 0.1 is 10. So I have 10 pi. 25 times 0.2 is 5. So I have plus 5 pi here. So that means that my error for the volume could be 15 pi feet, which is about 46 feet. Which that's kind of surprising because we had such a tiny, such an accurate measurement for our radius and our height, but even with an accurate measurement there, our volume could be 46 cubic feet off from what we expect it to be. So tiny measurements in one place could lead to large errors in other place. That's what the total differential here reveals. All right, well, it looks like I'm out of time, and I would say I'd see you next time, but I won't unless you're in my recitation. So have a good weekend, and yeah, thank you.